For decades, the Tokaido Shinkansen transformed travel across Japan. Success, however, created a challenge no engineer could ignore. Increasing train frequency could no longer solve the problem. Capacity, not speed, had become the nation's biggest transportation challenge. Engineers faced a difficult decision: expand an already successful railway or design an entirely new transportation system. The answer was extraordinary: build an entirely separate railway designed specifically for magnetic levitation from the very beginning. Choosing a new railway solved one problem, but immediately created another. Where could it possibly be built? The shortest route crossed Japan's most difficult terrain, forcing engineers to rethink almost every traditional railway design principle. Every measurement taken here would influence thousands of engineering decisions long before construction even began. Surprisingly, the mountains themselves were not the greatest obstacle. The real challenge was hidden beneath them. Before a single tunnel could be excavated, engineers first needed to understand millions of years of geological history. Only after understanding the mountain could engineers begin preparing to enter it, marking the true beginning of one of Japan's most ambitious infrastructure projects. Japan's engineers quickly realized that building around the mountains would create problems far greater than building through them. Every additional curve would reduce speed, increase maintenance, and compromise the very purpose of a next-generation railway. Speed demanded straight lines. Geography refused to cooperate. The solution was counterintuitive. Instead of reshaping the mountains, engineers decided to disappear beneath them. More than 80% of the entire railway would ultimately travel underground. Building underground dramatically increased construction costs, but reduced countless challenges above the surface. Before excavation, engineers needed to understand not just the mountain's shape, but everything hidden inside it. Every rock layer, fracture, and groundwater pocket would influence decisions worth millions of dollars. Only after months of investigation could engineers finally decide how each section of mountain should be excavated. The route had been chosen. The geology had been studied. Now came the moment every engineer had been preparing for. Months of planning ended the moment the cutter head touched solid rock. From here, every meter had to be earned. Every rotation of the cutter head reveals geology that no computer model can predict with complete certainty. Even a small change in rock quality can alter excavation speed, tool wear, and project costs overnight. Beneath the mountain, time is measured less by hours than by millimeters of controlled progress. Excavation is only one half of tunnel engineering. The mountain must also be prevented from moving. Water hidden inside fractured rock can become just as dangerous as the rock itself. Every liter of groundwater must be managed before permanent construction can safely continue. Deep underground, fresh air becomes another engineered resource rather than something nature provides. Behind every advancing meter, an invisible logistics network keeps the entire operation moving without interruption. The tunnel was finally taking shape, but excavation alone would never create a railway capable of carrying a maglev train.
Lifting the rebar.
As the cutter head moved forward, another engineering team immediately began transforming exposed rock into permanent infrastructure. Waterproofing may never be seen by passengers, yet it protects the tunnel throughout its entire service life. Concrete segments do far more than form a tunnel wall. They permanently redistribute enormous geological forces. Even after installation, every segment must still prove it meets strict engineering tolerances. Every completed section becomes the foundation for every kilometer still waiting ahead. Only after structural integrity was confirmed Could engineers begin preparing for railway construction
The
itself?
alignment is perfect. to within a
Surprisingly,
millimeter.
digging the tunnel was no longer the
Coordinates
greatest
verified.
challenge.
This control point
Precision
is
had
locked.
become the new
The
priority.
alignment is perfect.
Every future guideway position would depend on reference
Let's
points
finalize the
established
data
with
upload.
extraordinary accuracy today.
The laser is locked.
Millimeters
We're
measured here
verifying
would
benchmark
later determine
consistency now.
stability at more than 500 kilometers
Alignment
per hour.
confirms dead center.
The
The
mountain
team is
had
verifying
finally
the
been
laser
conquered.
alignment points.
Now, an even greater
To
challenge
ensure
would
the
begin:
markers are perfectly
building the
spaced.
world's most
Verify
precise
the lead on
railway
benchmark
inside it.
Confirmed. The lateral
The mountain was finally stable.
Proceed to the next
Now,
section.
engineers faced an entirely
The
different
alignment is
challenge:
locked.
building a
Verify the
railway
distance
measured in
between
millimeters, not meters. Unlike conventional railways, Maglev demands extraordinary geometric accuracy long before a single train can move. Every reference point becomes permanent. Every future measurement depends on these invisible engineering anchors. A mistake of only a few millimeters today could become a serious problem hundreds of kilometers later. Precision isn't achieved by measuring once. It's achieved by measuring the same thing again and again. Only after every control point is verified can construction crews begin installing the concrete guideway itself.
Check the lateral eyes.
Unlike traditional tracks, this guideway becomes part of the train's propulsion and guidance system. Every component must occupy exactly the position defined months earlier during geological and survey investigations. Heavy machinery built the tunnel. Precision instruments will determine whether Maglev can truly succeed. The guideway had finally begun taking shape, but the railway still lacked the technology that would make levitation
The
possible.
readout is 3 microns.
The guideway was structurally complete, but without electromagnetic propulsion, it was still nothing more than precisely shaped concrete.
Millimeter adjustment completed.
Unlike conventional railways, the motor is not carried by the train. It is built directly into the guideway. Each stator section must align perfectly with every section before and after it across the entire railway. Precision here is not simply about construction quality. It directly affects how efficiently the train can accelerate. Every completed section undergoes another round of verification before electrical installation can begin. Only after mechanical precision is confirmed do engineers begin installing the electrical part of the Maglev system. Thousands of stator coils must function together as one continuous motor extending for hundreds of kilometers. Every electrical connection is inspected repeatedly because reliability matters far more than installation speed. For the first time, the guideway begins to resemble the propulsion system engineers imagined years earlier. The railway could finally generate motion. Now, engineers faced the challenge of controlling it with absolute precision. Years of construction had led to this moment. For the first time, engineers prepared to energize the guideway itself. Every electrical zone is energized one section at a time, allowing engineers to isolate problems before they spread. Thousands of sensors now begin reporting temperatures, alignment, electrical performance, and system health in real time. Before carrying passengers, the railway must first earn the confidence of the engineers who built it. Only after countless successful system checks can the first test vehicle finally enter the guideway. Initial tests focus on stability and control, not maximum speed. As confidence grows, engineers gradually unlock the railway's full performance one carefully planned test at a time. Reaching extraordinary speed is impressive. Repeating it safely every day is the true engineering achievement. Decades from now, passengers may remember the journey. Engineers will remember the millions of decisions that made it possible. The Chuo Shinkansen is more than a railway. It is a national investment in technology, resilience, and the future of transportation. By opening day, the Chuo Shinkansen will represent decades of engineering, political decisions, and one of Japan's largest infrastructure investments. Critics questioned the enormous cost.
The completion
Supporters
portion
argued that future generations would inherit the benefits for more than a
high-speed
century.
Maglev technology.
History shows that transformative infrastructure often appears expensive before it proves indispensable. Beyond speed, the project's greatest achievement may be the engineering knowledge it leaves behind for future generations. Every tunnel, every measurement, and every engineering decision contributed to something far greater than a railway. They shaped the future of transportation.